lies at the outermost reaches of the universe. And what occurs when we endeavor to reach that boundary? You might ponder, how can the universe have an edge if it is boundless? This topic is widely discussed, and commonly people assert one of the following: the universe encompasses all space and time that exists. Indeed, that is a singular interpretation of the universe. The universe encapsulates all the spatial and temporal dimensions in existence. However, is it genuinely within our universe if we can never engage with it? Moreover, what if the realms beyond our universe vastly differ? The universe is deemed infinite because, according to general relativity, it is visibly flat, thereby indicating that galaxies extend indefinitely. But how precisely flat is it? Can we truly gauge the universe's curvature with absolute accuracy? And my personal favorite, given that it is beyond our ability to discern and test, is deemed beyond the realms of scientific inquiry. Before we delve too deeply, let's discuss the boundaries of the universe and the potential journey to reach them. The observable universe spans a diameter of 93 billion light-years and a radius of 46 billion light-years. Additionally, we'll explore the cosmic microwave background, CMB. Now let's begin with that 46 billion light-year measurement. This value represents the current radius of the observable universe. It denotes the distance to the CMB, the farthest observable entity in that direction. However, it's crucial to note that the actual distance to the CMB blob is not precisely 46 billion light-years. Currently, the blob has evolved into galaxies or galaxy clusters situated 46 billion light-years away from us, propelled by the universe's ongoing expansion. This expanse is known as the particle horizon of the universe. It signifies the immediate distance to the farthest region of the universe that could have a causal connection to us. Everything within this particle horizon constitutes the known universe. When I mention the current instantaneous distance, I refer to the distance you would need to traverse only if the universe halted its expansion and you traversed through static space. In cosmology, this instantaneous distance equates to the proper distance between 2 points, although nothing ever traverses this distance precisely. The shortest path in spacetime follows the geodesic, the trajectory of light between 2 points. Even light requires time to complete its journey, necessitating the inclusion of the time interval, particularly when space undergoes alterations. Journeying to the particle horizon necessitates navigation through expanding space. As we approach our destination, the expanding space will have stretched over the remaining distance. How far would you need to travel? Unfortunately, the answer is infinitely far, even if you're aboard a spaceship capable of traveling at the speed of light. Just like black holes have event horizons, so do universes. The event horizon of a black hole marks the point beyond which we can never receive information because light from that point is redshifted into oblivion. It serves as a boundary to the observable universe. There exists a region in this universe from which we can never receive any new signal, particularly one emitted today. This is because the distance the signal must traverse to reach us will be expanding at a rate faster than the speed of light before the signal arrives. The same principle applies to our light-speed spaceship. We can never reach anything beyond the cosmic event horizon because that space will be receding from us faster than light before we reach it. Now, things get peculiar. The event horizon of the universe is closer to us than the particle horizon. Based on our best estimates of cosmological parameters, we believe that the cosmic event horizon is approximately 16 billion light-years away. This implies that there are galaxies visible to us now that we could never reach or communicate with. We're observing ghostly images from beyond the part of the universe with which we can interact. As our universe continues to expand, more and more of it will cross the event horizon, and eventually, nearly all of it will be lost to us forever. It's rather melancholy. However, if we can somehow surpass the cosmic speed limit, then all bets are off. Let's explore that possibility. There's no question that Einstein was correct in establishing that limit for objects traveling through space. However, two regions of space can have superluminal relative velocities. This concept motivates the development of the warp drive. If we were to instantaneously travel to the particle horizon, we would witness the Milky Way as a small, infant CMB blob on our new particle horizon. Presumably, we would also observe a similar distribution of galaxies and clusters surrounding us. But what lies beyond that boundary? Well, it all hinges on the geometry of the universe. On the grandest scales, space-time appears very flat. While it may seem bumpy on smaller scales due to stars and galaxies, it's remarkably smooth on larger scales akin to ripples in the ocean. The distribution of galaxies and the CMB measurements support this flatness with extremely high precision, though not infinite. If space-time is indeed perfectly flat, then according to a simplified interpretation of Einstein's equations, the universe would be infinite. This assertion is frequently made, so if it holds true, what occurs once you cross the particle horizon? The universe simply extends endlessly. Consider it like this. The Earth's surface appears mostly flat to us because we lack the ability to perceive curvature locally. However, gain some perspective by journeying aboard the International Space Station, and its curvature becomes evident. What if the universe's curvature is so slight that we simply lack the capability to observe it accurately? It's possible that the universe possesses a curvature just within the uncertainty range of our most precise measurements to date. If this curvature is positive, it could imply that the universe is the surface of a hypersphere, the three-dimensional surface of a four-dimensional sphere. In such a scenario, our spaceship would eventually circumnavigate this curved hypersphere and return to its starting point. Now, how vast would this journey need to be? According to a recent estimate of the universe's minimum curvature radius, you'd have to travel at least 18 times the distance to the particle horizon to complete the loop, assuming the expansion of the universe remains static throughout the voyage. Additionally, we must acknowledge that these geometries are based on the most simplistic interpretation of Einstein's equations. Furthermore, while general relativity is fascinating, it doesn't provide a complete explanation of the universe. Some reasonable hypotheses about the origin of cosmic inflation suggest that our universe might be just one slowly expanding bubble within an exponentially inflating multiverse that extends infinitely. Bubble universes, regardless of their internal geometry, could potentially be finite in size, implying the existence of a true edge. But what lies beyond that edge? Are the laws of physics the same, or do we encounter a different number of dimensions? Share your thoughts in the comments below. For a scientific model to gain acceptance as a theory, it must make numerous independent and accurate predictions. Few theories have as many independent and accurate predictions as general relativity. For instance, the predictions made by general relativity regarding planetary orbits can be used to calculate the mass of the Sun, and this mass accurately predicts the deflection angle of light passing near the Sun, known as gravitational lensing. Similarly, when we study galaxy clusters, we can determine the mass of dark matter within them by analyzing the orbits of galaxies. Remarkably, the mass inferred from galaxy orbits matches the mass estimated from gravitational lensing. This brings up an important distinction. Dark matter is cold and clumpy, allowing it to coalesce into galaxies, but it lacks any interactions beyond gravity. Consequently, there's a limit to how dense it can become. Unlike ordinary matter, which can cool and collapse into stars, dark matter remains diffuse, because it doesn't radiate energy in the same way. As a result, it remains spread out rather than condensing into compact structures.